mainly couple of things. One is we said basically d lambda by dt, which is also indirectly d of n phi by dt, where phi is the flux linkage, E is actually E. If we are looking at only the induced EMF, which is in the inductance, which is there in the inductance. So, I can write the same thing as L di by dt if I am assuming that the inductance is a constant. If there is no movement in the electromechanical system, what we considered earlier. So, we considered basically a system somewhat like this. We had looked at a core which is actually C-shaped, and we also took one more maybe rod kind of structure which will be attracted by this electromagnet if sufficient current flows through this. So, let us say I have a coil, and if I have a sufficient current flowing through this, then I am going to have the electromagnetic force that is created is going to be quite strong enough, and it will go against whatever is the spring action I may have here. So, I am showing a spring which is attached to a frame. So, this is spring. So, we said that when there is no movement, the entire electrical energy that I am feeding in, which I may call actually as EI dt integral. I may call this as EI is the power. So, if I integrate it over dt or whatever is the time interval that I have, then I may call this as the electrical energy input. So, this is electrical energy input. Right? So, this will essentially go towards increasing the magnetic field energy if there is no mechanical movement imparted. So, I am going to say normally under general circumstances dWe equal to dWf plus dWm, where this is the mechanical energy, this is the magnetic field energy, and this is the electrical energy. So, we are looking at electromechanical energy conversion system where electrical to mechanical energy conversion is taking place, which is like a motor or an actuator in this particular case. So, if I am going to have no movement, this will be equal to 0 if there is no movement. So, I will have dWe equal to dWf, and that is what we wrote as, rather than writing EI dt, I can write the same thing as I d lambda integral, because dE by dt I can say, rather d lambda by dt I can call that as E, because of which I can say E dt is equal to d lambda. So, I am writing this like this. So, we said dWf equal to I d lambda in the case where movement is absent, motion is absent. So, we call this as the field energy. I am just recalling what we did in the last class, and we said if we are actually plotting a graph between I and lambda, we are probably going to plot it like this with non-linear characteristics. If I say that there is an iron core which is contributing to non-linearity between the relationship between I and lambda or n phi. So, I am going to call this portion as energy or field energy, which is Wf, and I am going to call this portion as co-energy or Wf dash. So, I may say that Wf is equal to I d lambda for a given position of the moving part. If I do not have any movement, it is at a given position, then I may say at a particular x value, WF is ID lambda and WF dash is actually equal to lambda di integral. And energy has at least some kind of physical connotation, whereas co-energy does not have any clear physical connotation. So, if I may say that it is a linear system which has linear characteristics between I and lambda, I am going to have essentially whatever is this rectangle that represents directly lambda times I. So, in this case, this particular line divides this area under the rectangle exactly into two halves. So, I will have energy and co-energy to be equal to each other. So, whenever I consider a linear magnetization characteristics, I am going to have WF equal to WF dash. So, only in linear systems this is going to be true. So, I can say in linear system I am going to have WF equal to WF dash. Right? After this we started considering a small movement. That's where we left off actually in the last class. So, let us again look at the system what we had considered. So, this is actually the iron core and I am going to have a current pass through this. So, the current is I. And the linear system is where there is no saturation that has happened. It is still in the linear portion of the magnetization characteristics. So, if I look at I versus phi or lambda versus I am going to have only a linear relationship between them. That will be true for lower values of I provided I neglect hysteresis. If you consider hysteresis, it is not linear anymore. I hope you understand. Because hysteresis will always talk about some amount of remnant flux density. So, if there is a remnant flux, the linearity is lost. Okay? So, I will not have, when I is 0, the flux will not be 0 if there is a remnant flux. So, I can't say it's exactly a linear relationship. After that also, once the saturation creeps in, as you say, if the I value is very large, at that point again it is non-linear. So, we are neglecting of course hysteresis property when we are talking about this, right. So, if I am looking at a system somewhat like this and I have, let us say, a moving portion like this which is attached to a frame through a spring, right. And let's say I have a distance of maybe x1 at this point in time. Rather, I am calling the air gap length to be x1. And let us say I am passing sufficiently large enough current through this, because of which the magnetic field created is strong enough to pull that moving part towards itself. Because of which maybe the distance has reduced now from original value of x1 to a smaller value which is x2. So, the movement has taken place in such a way that from x1 the distance or the air gap has decreased to x2. So, if I try to draw the two magnetization curves corresponding to these 2 points, this is I and this is, let us say, lambda. So, for x1, if I draw a magnetization characteristics like this, x2, considering that the air gap is lower, I should probably create a little bit higher flux or flux density, hopefully, because I am essentially looking at the distance decreasing, the air gap decreasing, the reluctance decreasing, because of which I should have the flux increasing slightly. So, this corresponds to x equal to x1, whereas this corresponds to x equal to x2. And let me assume probably that the movement is taking place pretty slowly. How slowly is a matter of detail very clearly, but let's say I have a time constant, electrical time constant for this circuit, which is L by R, some L by R. So if I am allowing the movement to take place slowly, the current can reach steady state at every point in time. And considering that the resistance of the circuit is a constant, the current can remain as a constant. What I mean is, I am giving sufficient time so that the current almost persists at a constant value no matter what. That means the time constant of the circuit is going to be much smaller than the time taken for the movement. That's what I'm assuming. So let me take a case where the movement is slow, which means the time taken for movement is actually greater than or much higher than the electrical time constant, so that I would not see really much of variation in the current at all, right? So I'm going to look at one particular current value coming up like this. Maybe I'm just taking I equal to constant in this particular case. Right? If it is an alternating current circuit, I have to look at I RMS to be a constant ultimately. Obviously, in an alternating current circuit, you can't expect the current will be a constant from instant to instant. So I'm looking at maybe the RMS value of the current is a constant. That's it. So under this situation, I will have actually two different values of lambda. Maybe this is one lambda value, which is the final lambda, which I may call as lambda 2. And let me talk about another lambda value, which is actually somewhere here, which is actually lambda 1. Let me write these points or name these points as O, this is P, this is Q, this is R, and this is S. So I'm just naming the points as this. Okay? Now, what actually I have input to the entire system is the electrical energy input. What I have given as the electrical energy input is the input to the entire system. So that will be from what we said earlier, EI dt. This is the electrical energy input. And after all, E dt we said is d lambda. So I have to integrate this as an electrical energy input going into the system as lambda 1 to lambda 2 I d lambda. That's all. Please remember the same I d lambda happened to be the field energy provided there was no movement. Now there is movement. So I am writing the same thing now as the electrical energy input, which actually I can specify as the area under this particular rectangle. Because I have to write this as actually lambda 2 minus lambda 1 multiplied by whatever is the current. Or I may say area of the rectangle, which is actually PQRS or PQSR, whatever. That is the area which is representing the electrical energy input during this particular duration of the movement, complete movement that has taken place. Yes. We are essentially writing only the boundary curves. We are not writing in between curves. The curve which is corresponding to OP, that represents the initial condition. And whatever is OQ, that represents the final condition. So the flux linkage has changed from lambda 1 to lambda 2, while the movement has happened from x1 to x2. So we are looking at the two end points, and then we are trying to see how much of mechanical work has been done. So we are taking stock of the situation after looking at the initial condition and the final condition. Last class we wrote dWe equal to dWf plus dWm. We are going to look at how much is the change in field energy, how much is the change in the electrical energy, or how much is the electrical energy input, and how much is the mechanical energy contribution. So we are looking at every single thing in this equation. So the electrical energy input we have accounted for as the area across that shaded portion. Whatever is the area of that shaded portion, which is corresponding to EI dt integral. That is electrical energy input. Let us try to look at whether there is any change in the field energy. We said field energy under a given situation is integral ID lambda. That's what we said. So if I try to look at actually the field energy, in the first case, I should have actually this as ID lambda, this entire area. That is what is ID lambda corresponding to the first condition where I have had the moving part at a distance of x1. So I should say corresponding to, or I can say initial field energy is actually OPR. This is the area. Right? Please note that it is OPR, that entire area enclosed by the magnetization characteristics corresponding to x1 and the lambda axis itself. Right? Whereas, if I look at what is the final field energy, right? That is going to be actually OQS. This is the area which is representing the final field energy. So if I want to get the difference in field energy, in that case I have to minus whatever is the final field energy. So I can say delta WF or dWf will be whatever is the area which is OQS minus OPR. Right? Is that clear? So these two areas, whatever is the difference, that is going to be my difference in the field energy. So I can say from here, this is actually area of PQRS, right? Equal to, this is area of OQS minus OPR plus dWm, which is the mechanical energy. So I should be able to write the mechanical energy finally as, that is, so from this equation, I should be able to write dWm equal to area PQRS plus area OPR, because this minus, when I get it to the other side, it will become plus. So that is this entire area. Are you getting my point? This entire area is actually area PQRS plus area OPR minus area OQS. That's what it means. Right? So if I look at the entire area, I am getting this entire area as the total area which is enclosed by the summation of these two, minus whatever is the area that is actually taken up only by this portion. That is, if I have to, I have made the figure amply shabby, but anyway, I can say basically this area I have to minus until this portion, which means I am going to get only area OPQ. So area OPQ will represent, area OPQ will represent, so this is area OPQ. Let me try to probably redraw the figure in the next thing. What we had done is, first we showed one curve like this, we showed one more curve like this, and we showed this I to be the same I, and we showed that this particular area, that is this rectangular area, gives me whatever is the electrical energy, and this particular area, whatever we have got, this area is going to give me whatever is the field energy originally that was present. So I have added those two, but the final field energy present is only this area, if I am talking about this as the area. So this particular area, that is, which is enclosed by the two curves, right? So if I may call this as OPQ, this essentially represents whatever is my actual value of mechanical energy that has been outputted by the system. So the mechanical energy output that has come out of the system when the movement has taken place from x1 to x2 corresponds to this area. Now we'll have to check what is really this area. We said basically this portion is WF. This entire portion is WF, whereas this is WF dash. That's what we said earlier. So if I look at what was WF originally when the curve was in P, or the operating point was in P, this was all WF and this is all WF dash. Whereas now if I am looking at only this, the portion above this curve is WF and below that is WF dash. So this essentially gives me the increase in the co-energy. Although co-energy does not have any physical significance, when the system moved from x1 to x2, whatever was the increase that happened in the co-energy, which is WF dash, that is represented by the shaded area. So the shaded area actually represents increase in co-energy of the system. So I can say basically this is dWF dash. The two together, actually I am getting the electrical energy input. That's all I am saying. So my electrical energy input is going towards two tasks. Rather I should say three tasks. One is resistance loss. Definitely there will be resistance loss whether I like it or not. The second task it is doing is to increase the field energy. Apart from that, whatever is left over, it is going towards mechanical energy conversion. Alone. That was because the movement was zero. We don't know whether it is the same input. That's a big question mark, because we considered actually the lambda is changing from 0 to particular lambda value, and we integrated the whole thing and we said area under that curve between the lambda axis and this was, your field energy. But now we don't know how much is the electrical input. We are saying, okay, there is some electrical energy input. We have not quantified anything. We have roughly said from lambda 1 to lambda 2, the flux linkages have changed. That's all. We don't know whether the quantity is the same in the previous case and this case. In the previous case, we considered there was no movement. We considered only one particular magnetization characteristics. Whereas in this particular case, we have considered two magnetization characteristics. One at length x1 and the other one at air gap length of x2. And we considered x2 is smaller. That's the reason why we considered that curve above the previous curve. Assuming that the reluctance is smaller, because of which the flux should be hopefully larger. Right? So this essentially tells me, right? I hope your question is somewhat clarified, if not completely. We are not violating energy conservation principle very clearly. In the last case, we didn't consider any movement. So the mechanical energy was 0. In this case, the mechanical energy is a non-zero quantity and we are trying to quantify it. In the process of quantification, we looked at different areas as per our definition. And then we ultimately arrived at the fact that we are getting the difference in the co-energy or increase in the co-energy is equal to the mechanical work done. So, yeah. If we are doing it slowly, automatically the current will remain as a constant, RMS value. Current is not really controlled by you completely unless you are varying some resistance or something. We are telling right now that the resistance is a constant. The inductance is changing. Clearly for every change in inductance there will be a transient. No doubt. But we are doing it so slowly that the transients are not so visible because the time constant happens to be really small as compared to whatever is the movement, the rate of movement. You are keeping the voltage constant, your current remains as a constant because you are allowing it to reach steady state at every point. The reluctance is changing, the inductance is changing, but transient wise it will change. You are allowing at every point the current to reach steady state. As simple as that. So that's why we said right in the beginning, if you are considering a slower movement, the mechanical time constant generally is much higher than the electrical time constant. You can consider either way. Here, even if we consider AC current, we are looking at the RMS value. If you actually consider DC current, you have to again consider the time constant there too. So I am passing a current. Let's say it reaches a value of say V by R. Okay? At that point, you are actually trying to move. When you are moving, you are going to see a variation in the current instantaneously. But you allow it to settle again and again. I would say it is better to look at an AC current in this case because we are looking at the induced EMF, d lambda by dt and so on and so forth. AC can reach a steady state. You call AC steady state as the steady state when you consider R plus j omega L as the impedance. You cannot talk about otherwise omega L. Please understand the phasor diagrams that you draw are for steady state. They are steady state. If you still have doubt, please put this into your head that what we are talking about as impedance as j omega L or 1 by j by omega C, all these things are in steady state. When you talk about transients, that is R plus, L di by Ri plus L di by dt. When you write that, that is transient. At steady state, the current should not change is your perception. That is not steady state. If the initial value at the beginning of a cycle and the final value at the end of the cycle are the same, you call that as steady state. Steady state does not mean it is not a constant. It should be a constant. No. You have simple harmonic oscillations. Don't you say it is steady state. It is oscillation. Of course it is oscillation. But it is steady state. Please understand. So, if I have an LC oscillation, I would say it has reached steady state very clearly as long as in the beginning of the cycle and end of the cycle, the values are the same. Is this clear? So, sinusoidal excitation, if I have, there is nothing like a constant value. Never ever. RMS values are constants. Yes. Fine. Right? Once it reaches steady state. We are having basically the flux is changing, reluctance is also changing. So, MMF can remain as a constant. You look at it that way. Flux is changing. It has gone from lambda 1 to lambda 2. Please note that. Right? Okay? it will clarify matters if you please read through PCSEN or any other machine's book once again from Electromechanical Energy Conversion Principle. So I would say dWf dash will be equal to dWm in this particular case. Now, this I can write as f dx, where dx is x2 minus x1 or x1 minus x2, whatever is the difference. So from this, I should be able to write f equal to, I am writing a partial derivative because Wf is actually, Wf dash rather is a function of both I as well as x. Very clearly, I can write Wf dash as a function of I as well as x, but I'm going to keep during this condition I as a constant, which means it is slow movement. Right? There is another case very clearly when I say there is slow movement, there should be some other case with faster movement. So maybe I would consider that case as well. Very fast movement, which is case 2. Again, I will compare this in terms of time constants. The electrical time constant happens to be maybe comparable or even greater than the way the movement is taking place, which is kind of very unrealistic. Because mechanical systems are normally pretty slow, whereas the electrical systems time constants are generally much smaller, generally, right? But let us probably take a system where it is a miniaturized machine, very, very small miniaturized machine. Maybe the inertia and other things will be really, really small, because of which the movement is taking place really, really fast. If the movement is taking place really, really fast, I can't assume now that I'm going to have I as a constant. Now the transient will definitely get into picture. So I am looking at again, let us say 2 graphs. One is maybe like this and another one probably like this. I'm just taking 2 graphs. Okay. Again, let me say maybe one of them is at x1, the other one is at x2. And let us say I am initially at an operating point somewhere here. Okay. And I is not a constant. So I am actually going to have rather flux as a constant. Please understand that generally the cause is I and the effect is lambda. Cause is I and the effect is flux. And it takes a little while for the flux to show up the change in the current. If there is a change in the current, you are going to have a little bit of time lag before it shows up as a change in the flux. That's why we call it as hysteresis. Hysteresis means lagging behind. The flux change always lags behind the current. So it's going to take a little while. But I'm doing the movement so fast that the flux linkage is not even given a chance to change. The flux linkage is remaining as a constant, you know, almost. I'm not going to have any change in the flux linkage at all. Let's say, I'm just arbitrarily taking some operating point and I'm showing that the flux is basically remaining, or flux linkage is remaining as a constant. Whereas the current is very clearly changing from, maybe originally it was I1 and here it is I2. There are 2 different points in the current. So the current has changed. That means the difference in the inductance in one sense is manifested in this particular case, because of which in the 2 cases the currents happen to be different. They are not the same. You are not allowing the current to reach the steady state. You are doing it so fast that the flux linkage is really not able to follow the, change in the position or anything. It's not able to do anything, basically. So, the time constant and the lag between the current and the flux, roughly you can say that, because the flux is manifestation of magnetism. The inductance, what you are actually putting it as a fictitious quantity, that is also manifestation of magnetism. That's why we write generally L di by dt as the voltage drop, which is also equal to N d phi by dt. That's why we write N equal to N d phi by di or N phi by I. So, inductance actually is a construct of human beings or electrical engineers who want to depict the relationship between magnetism and electricity in the form of a circuit. We wanted to do KVL, KCL, and KVL, KCL you cannot do unless you represent the magnetic field also as a circuit quantity. So the circuit quantity that you are manifesting by means of actually equating L equal to N d phi by di. So the Faraday's law came first probably, and then the inductance was introduced. That's how it was. So the inductance is basically the representation of the magnetism in circuit parameters. That's all. Okay? Fine. So we have here this as lambda. We already said that dWe equal to I d lambda integral. There is no change in lambda. So the electrical energy input is literally 0. Are you getting my point? We are really not getting any electrical energy input. So I have now two quantities only. One is dWf, the other one is dWm. These are equal to 0. Which means I'm going to have dWm equal to minus of dWf. Are we having a reduction in the field energy? Yes, very clearly, right? Originally our field energy was OPQ. Now I'm going to have maybe ORQ. So I should say WF at x1 is OPQ, whereas WF at x2 is ORQ. Right? So I am having a reduction in the field energy, and the reduction in the field energy is this shaded area. This is what is the reduction in the field energy, right, which is OPR. So this should be actually equal to area OPR in the graph. So I can say, in a nutshell, if the movement is taking place very slowly, the increase in the co-energy represents the work done. And if the movement is taking place fast, then the reduction in the field energy, that represents the work done. Right? Mechanical energy or work done. So I should be able to write in this case also dou Wf divided by dou x, where I'm going to have minus of dou Wf, of course. This is a function of lambda and x, of course. This will be actually the force with lambda as a constant. Lambda as a constant. So let me write these two expressions once again. Let me write that dou Wf dash, which is a function of I and x, divided by dou x, with I equal to constant, will give me the force. This is for slow movement. If I consider fast movement, under that condition, I'm going to have dou Wf, which is a function of lambda and x divided by dou x minus of this. That is the reduction with lambda being a constant is equal to the force. Yes. Mm-hmm. See, in this particular case, one second, let me just, okay. So you are saying basically that in the constant case, here lambda is remaining as a constant, agreed. Reluctance is essentially decreasing. So reluctance multiplied by the flux, which is actually also decreasing. So the current is decreasing as well, isn't it? The current is decreasing. Originally I1 is a higher value, I2 is a smaller value. It is very much fine. Why should it increase? Lambda multiplied by the reluctance. Reluctance has decreased. Lambda has remained the same. So lambda multiplied by reluctance is MMF. MMF has decreased. MMF has decreased. In the first case, MMF has remained probably the same, whatever, but here the MMF very clearly has decreased. Right? Okay. So we have basically seen that we are having an expression for the force that is developed in a translational system. What we have to study is about rotational system, because all our machines are rotating machines. We will look at it eventually. But before that, whatever we have specified as lambda, we said basically this is n times phi, which is also indirectly L times I. Provided we consider L to be a constant. If we consider L to be a constant, probably it is not going to have variable permeability even at a particular point. Then I can directly equate lambda, which is n phi, equal to Li, because we wrote like this, right? N d phi by dt equal to L di by dt, from which we wrote N d phi by di is equal to L. This d phi by di we are considering this way only because we are assuming that phi and I do not have a linear variation with each other. If I assume they are having an they are having continuously a linear variation, rather than writing d phi by di, I should be able to directly write that as n phi by I, directly, right? So if I am considering a linear system, I should probably be holding on to this expression rather than writing this in terms of calculus, right? So now we will look at the linear system, where we are going to look at all the quantities in terms of linearized magnetization characteristics, where we are going to assume n phi is equal to Li or lambda equal to Li. Thank you.